All right, this is Jack Creel, and I'm going to be discussing the calculation problems for this first week's homework. So the first one is trying to find the thermal conductivity of a material. And so we know when talking about conductivity, we're going to use this heat transfer equation. That's kind of hard to see up here, but we already have all the variables besides obviously thermal conductivity, aside from area, which is easy enough to calculate given the dimensions that were mentioned in the problem. And so once we have all that, the problem statement tells us that this is the total heat transfer. And since there's two samples contributing to that, we got to divide it by 2 first. And then we can set it equal to the equation above, rearrange for thermal conductivity, and we find that the thermal conductivity of this material is 0.781 watts per meter degree Celsius. And the next one, 1-72, is talking about heat loss in a section of pipe. And so we're going to use this convection heat transfer equation here. And it's talking about a really hot pipe going through a less hot surrounding area. So we put all the things we're given from the problem statement here. We still need to find the area, the surface area of the pipe. So using the properties given in the problem statement, we can do that here. And then using all of those pieces and plugging into this equation, we can find the overall heat transfer from the pipe to the surrounding, so the heat loss in terms of BTU per hour. And then in the next part, it wants us to figure out how much money this is going to cost us. So this is essentially just dimensional analysis here. We go from BTU per hour to BTU per day to BTU per year to therms per year. And then this process is 86% efficient, so we got to account for that there. And then the cost per therm is used here, and we'll end up changing this from BTU to hour to dollars per year with all the things given in the problem statement, and we'll find that just this heat loss to the surroundings is costing over $32,000 per year. 1-78 talks about a spacecraft and radiation heat transfer. So since it's radiation, we're going to use these two equations here. We have all the properties given from the problem statement here, and the problem statement tells us to set these two, the emitted heat transfer to set equal to the absorbed heat. And so we do that here. They're written out. We can cross out the areas because they're on both sides, the surface areas. And then what we're left with is this, which can be arranged for the surface temperature of the spacecraft, which is what we're after, and plug in all the values, and we'll find that the surface temperature of the spacecraft is 282 degrees Kelvin. These are both concept problems. The last calculation problem here is just talking about finding the binary diffusion coefficient for CO2 in a few different conditions. So the first one is at 400 degrees Kelvin and 1 atm, which we can just get directly from our handout, table 14.1. And we'll find that value here. And then for the next two, we can't do it directly because for part B here, we're after 400 degrees Kelvin and 0.5 atmospheres, but the table tells us in terms of 1 atmosphere, so then we have to use this relationship here to figure out how that coefficient changes with pressure. We can rearrange that, and pressure 1 is going to be the 1 atm we used above. Pressure 2 is the actual pressure of 0.5 atmospheres. Rearrange it, and we find the coefficient here. And then the next part is very similar, except now we have to go from 1/8 atmospheres directly from the table and use the same relationship to find the coefficient once it's at the actual pressure of 5 atmospheres, which is given here.